All right, so this situation, two charges, nanocoulomb charges, identical charges, 10 centimeters apart, and there's this point P out there, uh, 5 centimeters away. We want to know what the electric field at that point is. So let's take a look at things. So my goal here in the lecture is just to kind of pull things together a little bit more than maybe they were in the last one. And so what you're looking at here, this is just the definition of the electric field at point P due to um, the charge, 1 nanocoulomb charge, at least in the x direction. And so uh, this means we're calling this charge 1, and we're calling this charge 2. Okay, so that I didn't put that on the diagram. And the reason we know that that must be the case is, well, if we're talking about a 5 centimeter run here, and that's what I have a distance squared in there. So this has to be along the x-axis for the charge that is on the same horizontal line as P is. And we have, the K constant right here, Coulomb's constant, 9 times 10 to the ninth, or 8.99 times 10 to the ninth. It really doesn't make that much difference. All right. And then we have, 1 nanocoulomb. That's what's going on here. And this has to be along the x-axis because this is the x direction. Kind of obvious, I think. But just wanted to, I guess, more explicitly say what we mean, what the kinds of things you should be thinking when you use the equation. Um, in that regard, especially the electric field equation, it's about the field produced by something other than the location you're paying attention to. So electric field of charge 1, okay, um, we're talking about this charge. And it has some sort of electric field that emanates out that way. So this is, E1 is produced, since it's a positive charge, it's sending out its zoomies uh, in that direction towards, actually it's out infinitely many directions, directly away from uh, charge 1. So we have this application of the electric field equation, and then that produces this value of 3,600 uh, newtons per coulomb, which we'll find out later is the same as volts per meter. It's sort of like newtons per kilogram is the same as meters per second squared, just different viewpoint of that interaction. All right. So that was easy. When it's a straight line, you don't have to worry about anything because it's just the distance and along that thing. But since I have another, that's the contribution of charge 1 to the field at point P. But there's another charge in space in the surrounding vicinity, so now we got to deal with that one. And so again, we put everything in a Cartesian framework because that's the way we do the mathematics. We could put it in a polar framework, which can be understood in rectangular terms. We'd have conversions for that. You learn that in trig. But we're going to stick Cartesian here. And so it's still the case that the charge, of course, K, this is the same as K. We've been over that a couple of times. We usually don't bother with 1 over 4 pi epsilon naught, but that's the definition of K. So these are the same thing here. We're just emphasizing what K really is, but we typically just use the value. All right. Now in the video with Maxwell, if you remember the Einstein movie that you were supposed to take notes on, the thing that it boiled down to that I'll show later in the course is that's epsilon naught, and there's a mu naught for magnetism, same basic thing, but for magnetism. If you take the square root of 1 over the product of those two constants, that's the speed of light. That's what Maxwell derived from Faraday's law, Ampere's law, Gauss's law. Okay, and if it hadn't been for Faraday, it would have been a little later before anybody thought of that. But Maxwell and Faraday were collaborators, and basically Maxwell could do the math, Faraday couldn't. So that's the way that works. But anyways, so that little bit there, and if you uh, uh, so if we plug those numbers in, it's the same uh, charge value, still a 1 times 10 to the minus 9 coulombs, but uh, this r squared will be a different value that didn't get shown here. But if you take 0.1 and square it, and then divide that into the same thing as before, then you get this new value of 720. Now, there's a second part to this solution. All right. And so we want to think about this a little bit. So let's take our time. And so I want to take time just simply because, you know, you're taking notes. At least I didn't make you draw the pictures. All right. So in this setting, the distance, and of course I lost my point P, which is out here. All right. So we have this is the distance over which the electric field acts. And so one of the things we'll see in this set of examples is you always compute that r squared in the denominator is always the straight line distance. If it's off at an angle, then you have to do a sine and cosine part, okay, in order to obtain the fraction of that field force that you're going to use in your x or y sum of fields or forces, whatever we're dealing with. So the first thing we've got to do is figure out what that angle is. Or we could just have ratios of distances. That would work as well. But you'd still have to find this length. And that's not hard. 10 centimeters squared plus 5 centimeters squared is going to be some other number of centimeters squared, and you take the square root of that and you know your distance. Okay. But we could also work with the angle. Okay. So that's what we did in green there. The tangent of the angle would be the opposite over adjacent. And so we talk about the angle, this is the angle here. It has to be that because tangent is opposite over adjacent. And if 10 centimeters are going to be opposite, then 5 is going to be adjacent. So that's the angle we're dealing with. And we wanted to make that the angle because that's the angle at the point we're concerned about. If we had chose the other angle, we would be wrong. We would inevitably get the wrong multipliers. We were doing the right kind of thing, but not in the right location. So we want it to be relative to the observation location, which is where P is, and Q1 and Q2 are source locations. All right. So that's one little piece of the puzzle is when I'm dealing with an angle, I need to find that angle, or I could equivalently find all distances and then do cosines and sines. It'd be the same thing. All right. But we chose the angle here in this case. Okay, now we can take the components of the electric fields. Now we just worked out that the what the field due to charge 1 is. It was 3,600 or something, and that's it. Because it's along the same axis, E1 is done with the X part. So we already determined what that was. E1 in the Y direction, well, it's not acting in the Y direction at all. All right. What's the utility here? Since I have two charges, I have two fields that contribute to this location point we're paying attention to. Since I have that, and since it's something as at an angle, okay, then I must sum X fields and Y fields. So technically we don't need to compute E1 in the Y direction because it doesn't exist with respect to point P. Okay, obviously it does exist in reality, but with respect to point P, there is no field due to charge 1 in the Y direction that P notices. Okay, some other location would notice that. All right. So then let's take a look here. What in the world would this refer to? Well, that's 2 in the X direction. So basically, charge 2 has an E field that has its component. It would be a projection of E2. All right, so let me do this with the colors. So if this is E2, okay, then E2X is that blue part. Okay, it would be E2, which is that charge, 1 nanocoulomb over whatever that distance, square root of 10 squared plus 5 squared, or 0.1 and 0.05, because they have to be in meters, all right? And it's worth writing that, I guess. So this would be 0.1 meters, and this would be 0.05 meters. What would happen is you would have the right multiplier, wrong power of 10. If you didn't put it in meters, it always has to be length. Standard SI units are for length are meters, for force it's newtons, et cetera, et cetera. So that gives us the X part. And then the Y part, here would be what we see here, but E2, it's some multiplier of E2, all right? And so this part of the puzzle in doing electric fields and forces, or any field force is, or field or its force, is there's the way you compute the force when it's based on distance, which it totally is based on distance for this and gravity. But then when you produce angles in the Cartesian plane, then you take that force or field and you multiply it by whatever trig multiplier is the one that encompasses your source or your observation location. So that's been more implied than it's been explicit in prior discussions. Every example in every textbook assumes that, states that, but textbooks are hard to read, make your eyes blurry and sleepy and all that jazz. They do for me too. So it's a big club of people that get put to sleep by textbooks. So are we good on how we computed the 3 parts of the field that aren't zero? And the emphasis I want to put on it is compute the field magnitude, then take a look at, okay, do I need to deal with X and Y components? If you have an angle, yes. If you don't, then it's just going to be X or Y. Okay. If we really wanted to make this easy, we would have put Q2 directly under P. We would compute 2 fields and then do what's coming up shortly here. All right. But I just wanted to really take the slow road to how we pay attention to these angles. And we're going to do this. We have 11 examples. All right, so you're going to get good at this today. All right, and that'll help us as we move forward. Okay, um, so we'll really take our time today to understand this. All right, so we have that. The X and Y components of the net electric field. So we haven't computed the net. We've just computed the components. So the general approach will be, compute when you're dealing with fields. Fields will always play this way, a field force. You can compute the magnitude of the force because the field force is always going to be per unit distance squared typically. Okay, but it's always going to be that. There'll be a magnitude to compute, and then there'll be angles if it's offset from X and Y axes. If it is, then it's, okay, how do I get the net effect in this direction, X direction or Y direction? So that's what we're doing now. So we've computed the components. Now we're going to net them, if you will. So the net effect in the X direction is going to be those two that are in blue. So you have E1X, which we computed on the other page, E2X that we computed here, all right? And we come up with 3922. If you remember, it was 3,600 newtons per coulomb for E1, and then some fraction of that, okay? Also, it's the distance away. It's twice as far away, which means it's 4 times less because we're dividing by double the distance squared, all right? So that little 322 portion there got added in. That's the X direction. Y direction, same business. We have E1Y, which was 0, E2Y that we just computed above, 644 newtons per coulomb. So that was 720 was the field due to E2 at that distance, but the sign opposite over hypotenuse would be some large fraction of that 720. So it only bumps it down to 644. So now we've netted the component parts, okay? So now we need to, what's the net electric field at location P, because all of our component computations were done with a view to what's happening at P. Right? So that's simple Pythagorean. So here's, I'll learn to draw here, E1X, or E2X rather, I'm sorry. And then we have E2Y. Right? So we do all of that summing. So E2, or the net in the X direction squared, net in the Y direction squared, square root of that, and we get 3975 newtons per coulomb. That's the net effect. Right? Now, if we had gazillions of charges and we knew all the distances, we just tell the computer. This would be you could put this in a spreadsheet even. All right? Just put in distances, put in charge values, poof, 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 it's all done. And then now what's the angle of the net effect? Because it's being nudged at location P, there is, an effect due to E1, and there's an effect due to E2. Of course, that's a little off. Let me straighten that out a little bit. That's better, and that's I kind of made it large. It should be smaller. And it's going to be something like that because it's farther away. And those need to add up to something. All right. So the vector addition, we could do it graphically. And if those magnitudes are right size, then it'll point at this 9.3 angle. But the nice thing about any Pythagorean force netting, which is what you see there with the square root, if you just take the y part divided by the x part and inverse tan that, you get the angle that the net effect is at. All right. So we just have that down here in inverse tangent. We don't show the inverse tangent, but if you did the tan minus 1 of that, then that's where you get that, then theta or phi, both of them, whatever it is, will be that. So now we know the magnitude and the direction of this force, or this field. So if we were to write the net electric field, one way we could write it, we could say 3975 newtons per coulomb at angle 9.3 degrees. That would be a polar way to write it. Okay. If we wanted to write it in rectangular terms, we would need to do 3975 cosine 9.3. That'll be a number, and 3975 sine 9.3, and that would be the other number. That would help us write the graphical vectors proper size. Okay. So any questions on that? Hope that clears up a little bit of the puzzle of how we go through this methodically. I think what I hope you can see is that no single step in here was really, it was intermediate algebra, a little bit of trig, but it's stacking it. It's how you stack it. And if you get ahead of yourself, get sideways, then you'll do good math, but you swerved off the road of the problem and started solving some other configuration. All right, so the next example is the same setup, but now we're going to change the direction of one of the fields because that bottom charge now is pulling down. So this first part, identical to what we did before. The electric field at 1, same thing as before. Nothing new to say about that one. All right. And the magnitude of E2 is still going to be the same. All right. And instead of putting a sign, an SIGN sign on it, we're going to use English. Okay. It's 720 newtons per coulomb below the x-axis. All right. So just that English thing tells me if I can say along, I have no components to deal with. But if I have to say above or below, poof, I know I'm dealing, now I got to do that source requires components, period. All right. So you've already kind of taken those notes already, but this negative is going to obviously change our net effect as we move forward. And the angle will be the same as we saw last time. So we still have, our angle thing going on here. So if you wanted to say, same as last page, you could do that. We don't, none of this changes, same as before, but what you should notice is that now I have minus signs on X and Y components for source 2. And the reason for that is E2Y is pointing down now, and E2X is pointing left. So my net effect due to E2 is that way. So the below the x-axis turns into a negative, okay? And it has to be, notice that with respect to point P, if point P is at the origin, charge 2 is in quadrant 3, which has a negative x and negative y component. Hence, those two parts, the electric field due to charge 2 in the x direction has to point negative, and the electric field due to charge 2 in the y direction has to point negative. So I just put the negative sign on it. So the nice thing about this approach is that you can just use your English language based on observations and turn that into a mathematical thing, and you will be correct. Now the other option is you could have put in the angle whatever 270 minus 63.45 is. The cosine of that angle would give you a negative sign. It's another way to go about it. All right. For some people, that's preferred, but if you like English, the way we're doing it is more conceptually satisfying. All right. So here we go through the same net effect in the x direction. E1x remained unchanged, but E2x was a new deal. It was minus, you see E2x had this minus thing going on, okay? In the last example, it was added because everything was positive. Now that's a negative component, so 3600 goes down by that 300 and something or other. 322, I think it was. Same deal with the y direction, except here we just get the opposite of what we had last time. So the net effects in the y, E1, Y0 was nothing, but now E2 in the y direction was a minus. Because it was pointed down instead of up. Now, none of the signs matter with respect to the next computation, but the signs produced different magnitudes. Well, produced one different magnitude. The x magnitude was now diminished. All right. Whereas the y magnitude merely flipped its direction. All right. But again, negatives wash out when you do the Pythagorean net effect. So I think it was 3975 was the last one because it added, and now it's 3300 because of that negative charge at the bottom had a small pull away, 1/4 as big a pull, but in the opposite direction, pulling it down. All right. And then again, since one of the magnitudes changed, okay, and again, you have to use your noggin. You are not going to put a negative number into your tangent computation. You're just going to take the magnitudes. Because really, sine, cosine, tangent, in terms of if you're putting lengths in, there's no such thing as a negative length in trigonometry. Triangles just have positive magnitudes. And so when you're just doing these sorts of things for the sake of the angle, you wouldn't put negative in when you're dealing with length. You could put a negative angle in if you're trying to find an angle, and that'll give you a negative length, okay, if it's in the right quadrant. But here you just put the magnitudes of those in, and you get 11. All right. So what it is the so the y part didn't change the net. It's still above, but it pulled it down a little bit from 9 to 11. Yeah.
I understand what you're saying about the negative ones and the negative angle and whatnot, but if you think about it from the origin, like we were going to say, if we have a negative angle going in quadrant 3 or quadrant 4, then that could.
Well, what that would be is if I change the 6345 to whatever 270 minus that is, it would give me the negative for that component. So realize, the other way to do this, I'm glad you asked, would be I could write, another way I could write e2x equals e2 cosine of 206.55, I think that would be. Okay. That would give me a negative. It would give me the, well, yeah, that one would be negative. Whatever that is, it would be negative. I don't think we wrote it out. And then I would add that in my x net equation, and I would still get the same number. So it's equally good ways to think about it. For some folks, and it's important, if you're going to do an angle, trig circle, you have two choices, relative to an axis or the actual rotation from 0 to that location, right? One of those things. And then with the first one, you have to determine what the sign is. With the second one, it gives you the sign. All right, equally good ways to go. All right, so that's that problem. So it's the same problem. All I did was change the one of the charge signs. So one thing to get from this, we should have expected that angle would widen by some small amount. So we went from a smaller magnitude because it was a diminishing effect in the y direction. And so that 9-degree angle needed to widen out a little bit. Okay. And we would, how much it would widen out is hard to say what your natural inclination is, but you should expect that angle to change a little. Okay. All right. Next problem. So these charges here, I did bother to label them. Q1 at the top, Q2 and Q3 at the bottom. So there's a lot going on here. Okay. So here we're going to compute forces. We want to know what all the forces are going to be. So we are, if you skip down, I forgot to put in the question, but let's look down here to our final answer. So at the bottom of this, we want to know the force on 1 in the y direction. All right. And we were in the x direction. Why is it 0? Why is the force on Q1 in the x direction 0? Meaning, so charges 2 and 3 will exert a force on charge 1. So the question is, Let me type it in here. What? Oh, I don't want that color. What is the force on charge 1? Okay. Why is the force in the x direction 0? So the two bottom charges are pushing charge 1 up. And so they can do that in a number of ways. So there's the x part of that one and the x part of that one. But the y part, there's two of those. So the x component of those two bottom forces, they're equal and opposite. So the net effect in the x direction of the bottom charges on the top one is nothing. And the reason for that is one of them is directed right, a plus, and the other one's directed left, a minus, and they're the same magnitude because they're splitting that 1 centimeter distance with respect to charge 1. Because this question is about what's the force on charge 1. So down at the bottom, we just state that it's 0, but we don't necessarily need to do any math to show that that's the case. All right? And one reason we do show the math. I get a positive 0.9 force 2 on 1, and I get a negative 0.9 2 on 1 in that regard. So sort of skip to the end of the book on that one, because sometimes, I mean, I recommend you write all this out, but the note to put is, gosh, I don't even need to compute the x components. You should be able to look at the situation and go, well, they cancel each other out. And if they were minus, they would cancel each other out because the other one would point left and the other one would point right. And you would still have a plus and minus of the same magnitude, which along the x direction, net effect 0 for the two charges on the bottom and the force they exert on the top charge. So there's two ways to do it. The way that I started with was just to look at it and go, they're opposite, equal magnitude. The other way is to just literally obey the rule set of compute the forces, net the components, and see what happens. All right, so now that's what I'm going to start with. Here's Coulomb's law. Again, it has the same inverse square structure as the field, which is unsurprising because if I just divide by one of the charges, I have the electric field. Okay, and again, we're plugging and chugging away. So the force of 2 on 1, all right, that's going to be this right here, this big pink arrow. All right, the force of 2 on 1. All right, in fact, I really should, it's going to be more like this. Okay, because that charge wants to get pushed away along that same line. Important things to note, K constant, 9 times 10 to the ninth, and we're showing all the units there. Q1 is the 1 nanocoulomb charge. 2 nanocoulombs is the Q2 charge. And the distance squared will be, again, it has to be in meters. So 1 centimeter would be 0.01 meters, or 1 times 10 to the minus 2 meters, and you square that amount. All right. So we get this 1.8 times 10 to the minus 4 newtons away from Q2. Right. So that's the force magnitude, which, just like we saw with the electric field, is based on the straight line distance from source to location, observation location. Hopefully you've detected that when we get to the other charge, it has to be the same magnitude. Everything's the same. Charge magnitude is the same, distance is the same. Nice thing about an equilateral triangle, right? So when we get to that, we'll have that going for us. So that's force 2 on 1 in the x direction. Now we do force 2 on 1 in the y direction, all right? And it's just sine and cosines, all right? Nothing crazy here. That's just paying attention to the left side charge. Then F3 on 1, it has to be the same magnitude as the other one because it's all the same charge inputs. And then we're going to do the same business. Now let's be careful here. Notice that there's a negative sign here that wasn't there. So however you want to annotate your notes, why is the force 3 on 1 along the x direction negative? That's because it's right here. Okay, so we have a positive 1. When it was 2 on 1, it was positive. When it was 3 on 1, it's a negative. Just right, left. Standard issue. Right is plus, left is negative. So however you want to write that, note the difference between those two. One has to be plus and the other has to be minus when they're same charge sign. Period. Always has to be that way. If it was negative charges, they'd flip. The top one would be negative and the bottom would be positive. So down here in the bottom, the net effect in the x direction is going to be this one and this one, which computationally they're equal and opposite. We didn't need to do the math to show that. So I think it would be superior to not do the math and just go, oh, never mind. You could just write the second to last line and you've netted the x direction influence of the two bottom charges on the top one. Save yourself some scribbling. But you must pay attention to the y components. And the y components, unsurprisingly, the 1.56 and the 1.56. all right? They have to be identical. In the same way that the x components were equal magnitude, the y components have to be equal magnitude. Except in this case, they add to a non-zero because they're both positive up. So really, now that we've come to the end of the problem, if you step back and think, okay, the symmetry, I have an equilateral triangle, which means I have symmetry. No matter how you look at it, there's symmetry, okay? Especially since the top one is the only charge that's different, the bottom two are identical. So in the x and y directions, I have symmetry. The symmetry in the x direction is a net effect of 0. The y direction, I'm doubling whatever that is. And so literally all we really needed to do was double one of the y computation because they're both 1.8 18 millinewtons times sine of 60. There's some fraction of that field force along that distance. And that would be our answer. So 1.56 times 10 minus 4 Newton times 2. So just a little bit, a minute, it took me a minute to say that. And just go, gosh, all I do is if I just double one of those y components, I'm done. Because of symmetry. So I want you to have the notes as they're given because computationally that's valid. And if that's your, comfort blanket, then just do the math. But you can save yourself because the more math you write, the more likely you are to make a silly error, right? This is the way it goes. So if you can spare yourself, ciphering, spare yourself error, all right? All right. Let's
So actually, I do have a question about that. So if you were going to make that.
All right, let's get on to this next one here. Same situation, negative charge in the bottom. All right. So let's just go by the flow here. All right. Of course, we lose our symmetry in the x direction, but we're going to get the cancellation in the y. Because one's going to be up and one's going to be down, but in the y direction this time. So again, but just to stay with the flow of things, we start up here. Again, the question that I forgot to type in, what is the force on charge 1? So when you ask that question, you must consider those two things. The force on charge 1 is going to be due to the force of charge 2 on 1 and the force of charge 3 on 1. Okay? So if you wanted to, you could kind of give yourself some space and just write out, okay, these things. So this is kind of a qualitative approach that gets us to the quantitative. So, skip the lines between what I've highlighted and just kind of go with this thought pattern. Just kind of go down the middle of the page and write that. Okay? Because this is the thinking. And if you have right thinking always leads to right doing. I don't care what you're thinking about. Physics, math, life, right thinking leads to right doing. So the force on charge 1 is going to be due to the two charges that are beneath it. And so I can write force of charge 2 on 1, and that's Coulomb's law. It's going to be KQQ over R squared. And charge 2, the force of charge 2 on 1 is going to be Coulomb's law, and it's going to be away from Q2. It has to be, okay? Because they're they're like charges. All right? Down here, force 3 on 1, it has to be towards Q3 because they're opposite. They're unlike charges. So it's just a qualitative viewpoint of the force. We haven't even done the math yet. The only math here was symbolic, the standard classical Coulomb's law. This just sets our expectations. So immediately, the net effect is going to be off to the right there. It has to be. Because I have an up and to the right and a down and to the right. The net effect of that's going to be fully x direction to the right. So now I know, this is the power of just thinking it through for a second before you do math, is if you got something other than some small amount, smaller than either of the two force magnitudes to the right, you know you must have done it wrong. Okay? So that's the power of just thinking it through properly. All right. So now that we've done that, now we go to do the math. The physics, technically, at this point, the physics is done. The rest of the problem is a math problem. Okay? So we plug in Chugsville here, Coulomb's constant, charge 1, charge 2, and the distance between them squared. Still away from Q2. You plug and chug all of that, and you come up with this force magnitude. The magnitude of that force, and in this part of the puzzle, and this is probably worth an annotation, we're pretending that these are the only two charges in the universe. We're forgetting that there's this other charge 3 off to the right. All right? But since nothing is strictly x or y axis, excuse me, we know that we have to do components. But this is easy. The x component is going to be the cosine, and the y component is going to be the y, or sine. So we do these computations. We take this value here, and it pops down into there. And then we have a sine and cosine deal for this angle. That would be the other cool thing about the videos and the workbook is if you got a set of colored pens, you can mention it. Super nice. All right. So we've done the component parts for force 2 on charge 1. We're going to repeat the drill for the other charge. All right? Everything was positive on this one because it was pushing up and to the right. And that's the other thing about drawing the picture with the vector arrows. I know that I have to have positive answers. Because the x part's positive and the y part's positive. It has to be because it's pointing to quadrant 1. This next one's pointing to quadrant 4, which means x has to be positive and y has to be negative. So going back to your trig, you have expectations that you've drawn because you did a qualitative interpretation to set you up for the computation. Right?
That's thinking like a scientist, okay? A physicist in particular, but that same thinking pattern is all the science needs to go that way. You're going into some area of science. Based on your presence in this class, it means your thinking needs to be this way. All right. So the next part, force 3 on 1. 3 on 1 in the x direction. Well, let's do this. So force 3 on 1 ended up being that same magnitude. Surprise, surprise, since all the products are the same. But force 3 on 1 in the x direction will be that magnitude times the cosine of 60. Again, x parts are cosine, y parts are sine. And this negative right here has to be that way because it's going down. So if you wanted to, that's the force 3 on 1 in the x direction. All right, and force 3 on 1 in the y direction. That's why that's negative. It's going down. Could I put, 270 plus 60 and get a negative? Yeah. Or plus 30 rather, I guess, since it's bisecting that angle. That'd be another way to go. So we get our numbers, and so I have two x parts that are going to add to something that's not 0. This is the opposite of the last time. And I got two y parts that add to 0. Again, we detected that qualitatively at the beginning, but I wanted to go with the flow in this one since I kind of interrupted it in the last one, just to variety here. And so, again, the y parts, they cancel because this one, is going up. All right. So this is the F2 on 1 in the y direction. Right. And this would be F2 on 1 in the x direction. So a force diagram, the free body diagram gives us, that's a qualitative graphical approach that tells us what the math should look like, and can tell us, don't even bother with, I take that back. Screwed that one up, thinking of the last problem. These are a doubling here. All right, so in the end we get our what's kind of interesting is we end up getting the same magnitude. So the other reason I picked this problem was for this. We got as our net total force, since it's all x, was the same as either one of the forces of individual charges on 1. And the reason that we added up to the same value was because, well, sine and cosine of 60, are the same, you get the 1/2 business going there. So, little subtlety there that was by design, if you will. That one's in the bag. Well, everything got a little small. There's a lot going on there. So let's think this through. So again, again, same question as before. You know, what is the force on charge 1? And let's think through this statement here. So I'm going to go slow, so you're going to have plenty of time to copy this as we go. But this statement says that the force 2 on 1 equals the force 3 on 1. So let me, force 2 on 1 is going to be something like that. It's going to push it away because charge 2 is up there in the upper right-hand corner. Force 3 on 1, same charge interaction, a 2 nanocoulomb to a 1 nanocoulomb. It's going to push it away that way at the same magnitude. Force 4 on 1, from a magnitude standpoint, will be the same magnitude. Okay, so I'm going to switch here. 4 on 1 and 5 on 1, I'll switch to blue. Force charge 4, the bottom left-hand corner, it's going to do the same thing that charge 2 is doing. It's going to pull charge 1 to it with the same amount of force that charge 2 was pushing. And then charge 5 on 1 is going to be the same business. So just a little bit of upfront thinking. Here's the thing that you can see in the bottom line. I know it's going to go to the left because I have an up and to the left pull and a down and to the left pull, which is a net pull to the left. Okay? It won't be 0. It's going to pull it to the left. And the pull to the left will be smaller than any of the current pulls because the triangle has to be a smaller leg there. All right? So we'll find out here, well, the Y symmetry, it's pulling, the Y's cancel each other out, but the X parts will add in this. So the short answer there. So here's the thing. Since every charge interaction from a magnitude standpoint is a 1 nanocoulomb times a 2 nanocoulomb, every distance is the same distance because it's a square. And charge 1 is in the middle of the square. That means I have the same force magnitude no matter which interaction I'm paying attention to. So it's worth it to compute what that force magnitude is, especially since I know I'm dealing with components. All right? So that's what this first part is. Gives us, this force magnitude. So just a little note here. This distance squared bit is coming from splitting the square here. Okay, so those are both equal legs, and you have so this leg squared plus that leg squared is going to equal, the sum of those two things is that one squared, if you will. Yeah.
So it's listed as, in the negative 2. Okay, I just read it wrong. Yeah.
Right.
Okay.
So these would be, you could just write those as, 0.05 meters squared. That's just 6.1 and so that's going to equal some number, but that's going to be my my r squared. Remember, Coulomb's law is going to be k QQ over R squared. So this is our R. So that's a nice thing about having an inverse square. You deal with a triangle, just the sum of the squared sides will give you that you don't have to find R, then just the square root of the thing. There's no point in doing that. Or square root of the square root. Right. So we have our magnitude, all right, and so now it's going to be paying attention to directions. And I'm going to have all opposite directions for y and common directions for x. All right? So one by one, so here let's do this. I want to notice the magnitude showing up in all of these. Every one of these things is dealing with the exact same magnitude. And when we take them in pairs, so let's deal with force 2 on 1. Here, actually, let me switch to, so force 2 on 1 in the x and y directions. Okay. Need a little bit more space. Super simple. 1, they're both negative. And why are they negative? Well, if we go back to our red arrows over here, they're going to the left. It's pushing to the left here. Force 2 on 1 is pushing it down into the left, quadrant 3. So that'd be another way. You know, it's pushing in that direction. So we have that going for us, 2 negatives. Then let's see here. Force 3 on 1 in the x and y directions. So charge 3, it's pushing left in the x direction, but it's pushing up in the y direction. So its x is negative and the y has to be positive because of where it's pushing. It's pushing into quadrant 4, which is negative x and positive y, whereas the other one was pushing into quadrant 3, which is both negative. So there is some value, only in the realm of science, to knowing your quadrants and all that jazz. All right. Otherwise, it's just a math thing. But here it actually relates to something physical. All right. Then force, need more highlighter colors. 4 on 1. So force 4 is also pulling. The force is pointing to the third quadrant, which is both negative. It's actually pulling in this sense, attracting, it's an attractive force, but it's a quadrant 3, so both are negative. And then force 5 on 1 in the x direction, charge 5 is pulling to the left x-wise, but it's pushing up, therefore positive. Or it's not pushing, it's pulling it. So again, bunch of force magnitudes made plus or minus based on the direction, cosine for x parts, sine for y parts. And since it's a square, all the angles are 45. Okay, so same multiplier. Root 2 of 0.707, yeah, the root 2 is 1.41. So notice that all of the magnitudes are the same magnitude. Surprise, surprise. It has to be that way since the magnitudes of the force are the same, and since the angles are all the same, and in particular the 45 degree, we get one answer. So a shrewd and student of trigonometry would go, oh, in addition to only, so the shrewd physics students say I have one magnitude, okay, to deal with, just different angles, and they go, oh, the symmetry of a square means I really have one multiplier. So we could have multiplied the original magnitude by sine or cosine of 45 and had that, and then just go around putting plus and minus signs on that product. Again, wouldn't that be better than writing 8 lines? Yeah, because all you did was write essentially the same thing over and over again. And what was different? The SIGN of the magnitude in that interaction. All right? And since you can eliminate the Y net effect by symmetry, now all you need to know is how many times do I add the X part? And I know it's all additive because it's all to the left. Not one of them goes to the right. So, if we kind of zoom in on the X part, because that's the only thing that ends up mattering, I have this X part, that X part, all of the X parts end up being the same magnitude and direction, which we knew from our first swipe at just qualitatively paying attention to all the forces. All right? And so 4 times that would be the answer. And so we could have just started the problem, say, okay, well, it's going to be the force is all going to be left. It's going to be K Q1, Q2 over 1 distance squared, and it really wouldn't matter root 2 over 2. And we could immediately get to our 2.55 times 10 to the minus 4 newtons. And we'd come over here and we'd look at our force arrows and go, that's the magnitude of all of the X components, which are all that matter. So if I do this, they're all negative times 4. I get my answer. So we sort of needed to do the math to justify bypassing the math. Okay? But it is a better way to go. And it's one of those things, you could take some time to smell the roses. You go, oh, this is really an easy problem. It's not as complex as it may seem when you look at it. So has everybody captured all that they need?
All right. Let's do another distribution. Okay. And again, the question is, what is the force on charge 1? And just like all the other times, I have these 3 charges on top. Oh, I needed to, well, those both can't be Q3. So let's see, where, looks like the 6 is Q3 and the 2, well, Q2 and Q3 are, so now I got to fix this. So this should be Q4. Makes sense. Right to left, 2, 3, 4. So change your um, far left Q3 to Q4. So standard issue force is always Coulomb force here for these things. No surprise there. But what's going to be different is 2 on 1 involves that. 3 on 1 involves 3 and 1. And obviously 4 on 1 is going to involve charge 4 and charge 1. Again, you might want to just space it out, fill in the blanks as you go, because again, I'm doing the qualitative, just what's the lay of the land in this puzzle. So let's think about why it's away or towards, etc. So force 2 on 1 is wanting to push along this line. You know, this is force 2 on 1. It wants to push away. And so if that's going to be my magnitude for a 2 to 1, then I'm going to switch over to the far left, the 4 on 1. That's also going to be away from Q4 at the same magnitude. Force 4 on 1. And then the negative 6 nanocoulomb charge wants to pull charge 1 up. And so since it's at the same distance and the magnitude is going to be bigger, 3 times bigger, because 6 times 1 is 6 versus 2 times 1. So that means the force here, we'll draw it larger. This will be the force 3 on 1. Looks to me like charge 3 is going to win. I think there's more math on the next page after this. So we'll see how that goes. So now it's plug and chug. So technically at this point, physics is done. It's a math problem now. All right. And so we're going to deal with the magnitudes first, and then we'll get to the SIGNs after that. So the unsurprising value for Coulomb's constant, and then just the charge magnitude. So force 2 on 1 ends up being 0.72. 3 on 1 is a 2.16. Negative fifth magnitude. And 4 on 1, after you plug and chug, you get this 0.72 magnitude. So hopefully you're noticing that in this lecture, I am emphasizing find the magnitudes, then the components, and get your directions in the terms of plus and minus signs along that way. But first, just get that force magnitude. Okay. Now, one little side note that I haven't emphasized yet. This, when I write or when you read that you have force 2 on 1 equals Q1, Q2 over R squared, and these are all magnitudes. That's not a vector yet because it doesn't include direction. But if I write away from, otherwise I'd have to drop that vector arrow on F. If you don't see the vector arrow, it's not a vector. But if you see the vector arrow, it has to have a pointer, either in the form of an angle, a unit vector symbol, or the English that says the direction, satisfies as a vector. So just to kind of, why is that a vector? Or there's this vector arrow here in that regard. So we have our, yeah.
It says 2.16 times 10 to the negative fifth away from Q3 should be towards.
Yes, it should be. Good point. Hopefully the y direction is a positive, because that's all it's got. That's the nice thing about charge 3, one direction. The other two require an angle, and they'll be the same magnitude, different signs as we move. So let's look at the next part. All right, so I'm going to get the old highlighter going here. So let's deal with force 2 on 1, both x and y parts. So force 2 in the x, so I'm going to do the y one first. You know, it's well, so it's doing something like this, which consists of a y part and an x part. Both are negative. So these negative signs here come from the fact that it's quadrant 3. All right? We could just write root 2 over 2, because cosine and sine of 45 are just that value. All right? But we'll be explicit here. And so those magnitudes are equal, the x and the y parts. Then moving on to force 3, there is no x part to the force that charge 3 exerts on charge 1, because it's all directed down. Okay? Or vertical, rather. But the force 3 on 1 is a very large, comparatively, magnitude-wise, up. And we did get the SIGN right here, because it is positive in the y direction. Now force 4 on 1. So again, I need to change that Q3 to Q4 over to the left. This is going to be the same deal, but it's pushing down in the y direction and right in the x direction, which is why you have a positive 0.509 for the x part, because it's pushing it to the right just as much as it's pushing it down, which is why it's a negative for the y part. So when you go this path, you immediately see from the vector arrows that the x parts cancel, which is why the netting in the x direction gets you 0. You get 0 for the 3 on 1 part here, and you get 2 on 1 and 4 on 1 in the x direction are equal and opposite. So they drop out. Do we need to write it? Nope. You just look at it. All right, but the math is there. Some people that helps with the accounting. So all that's left at the end of the game is the sum of the y parts that we see here. and you have a negative. So basically, that's going to be 0.12 or 1.2 down, but you have 2.16 up. All right, so the 2.16 up, need to circle that better, obviously is going to win against the 1.2-ish down, giving you a net of 1.14. All right, so we knew it was going to be a net up, didn't know how much at the beginning. All right, so never mind that it's all at angles. The nice thing here is they were all same distance, so we could get away with that magnitude computation from the other. Two more, this one and the next one. This is going good. So now this one, in fact, the next two, this one and the next one, are designed to take us back to first semester thinking here. So this bead over here is suspended along a string at that angle because there's another charge, equal charge, on that stick. So this is basically another version of the sticky tape experiment. Right? We saw the same sort of interaction when we did our first lab in this stuff. So we get our things going here. So let's think about this statement up here. So this is a little bit of review. If I sum the forces in the y direction, okay, there's a tension, in this rope. We call that tension T. And the tension in that rope in the x and y direction is going to be some portion of, it's going to be a sine cosine of 45. So we're back to this nice multiplier. But in the y direction, I have an up force, and the part of that up force would be the cosine of 45. And the reason for that, and this is where it gets a little tricky, is in the y direction, ty is adjacent to the angle 45. Now, we would luck out in this case if you wrote sine 45. Oh, well, you'd be technically wrong, but you'd get the same number. Okay, so that'd make a good test question. And since it's not moving, okay, it's suspended, that means the forces are in balance. It means the net acceleration of the system is zero. We did a whole bunch of that last semester. And so the only two forces in town are the electric force and the gravitational force. Okay, so we continue here. So this tension, an up force, and a down force of the weight, minus mg, lead us to that the tension in the rope is just the weight divided by this fraction of the weight, or the angle that we're at. Okay, so root 2 over 2, which we'd rationalize that and get some multiplier, but we'll just leave that alone for now. So that was the y direction. Y component of the tension minus the only other y force in town, which is the weight. All right. Now the x part of forces is Coulomb's law. Okay. So and the Tx. So there's the x component of tension and Coulomb's law. Now, why is it Coulomb's law minus the tension? Well, Coulomb's law is pushing to the right, and the tension is pulling to the left. Okay? So they're opposed forces, and they're in balance because this is a no acceleration system. All right, so we continue our thing here, and here we don't solve for the same thing. I mean, we could, all right, but there wouldn't be much point in it. And I guess the question that we could ask is, what is the charge on the beads? All right. So since we've already solved for t, and we want to know the charge on the beads, it's good to get an equation that has q all by itself on the side of the equal sign. So we get our q squared, and then it's a math problem. And I'll just let you copy that. So you would take this piece and jam it in where t is, and the rest is math history. Last problem. Same basic situation. And again, what's the charge? So here we have two charged spheres, and this is sticky tape experiment explicitly, except with imagine two ping pong balls or something that we managed to charge on strings. All right. So 3 gram beads, spheres or whatever. So 3 grams, that's a good weight for a ping pong ball. It's plastic, it can take charge, and it'll distribute uniformly. The strings are equal length, and since the masses are the same and the charges are the same, they're going to separate at the same angle. All right. Any differences, and then we'd have a heavier ball, may not cooperate as well. All right. So there's static equilibrium. String makes 20-degree angle, 3 forces. So you have the tension in the strings. You have the weight of this. So the 3 forces acting on each sphere are the electric force, weight of sphere, and the tension force. So the electric force here weighted the sphere there, and the tension force there. Oops. So the net force, or otherwise known as the sum of all the forces, actually that shouldn't be the first law. Gosh, typos. That should be the second law. All right. They must add up to 0 since MA, the A is 0. It ain't moving. It's in static equilibrium. Sum of forces are 0, according to Newton's second law. All right. So let's bust this up in X and Y parts, because that's what we're dealing with. So over here, I have, here is a small simplification of the diagram, and then there is this force diagram for the right-hand sphere. Okay, so this right here would apply to that one. And obviously the other one would be identical except flipped across the y-axis. Okay, so one idea here. So let's jump into the x forces here. Netting on the x forces. So minus t sine theta. Why is it a sine? Well, this angle right here, opposite over hypotenuse. That's why it's sine. Okay, it'd be really important that we understand that the x component ends up being a sine because of where the angle is in our interaction. So generally speaking, x is cosine and y is sine, but don't fall for it. Okay. So the easy multiple choice distractor is, did the student do the standard x for cosine business instead of what the diagram actually specified? Okay, so that's the importance of drawing the diagram, is it gets you to the right. And then this time the angle would not be cooperative. All right, sine and cosine of 20 are going to be different numbers, unlike the 45 degrees. So weight force in the x direction, well, hopefully that's obvious that it's not anything but zero. Weight acts down, straight down. There's no inclined plane with a component of the weight force. It's acting straight down, period. So there is no x component to the weight. That's why it's zero. Hopefully it's pretty clear that there is a non-zero Coulomb force. It has to be non-Coulomb, and it's going to be uh, uh, positive because they're pushing out. Okay, so we get to that on our x component summing. Let's clean that up a little bit. Now the y component summing over here. The y direction tension is going to be a cosine. Since it was sine for x, it's got to be cosine for the y. All right. In the y direction, I have the weight is non-zero because that's the only direction that weight force acts. Okay. And there is no electric force in the y direction. Okay. Because these two, it's only this way. There's no electric force interaction directed upward, only horizontally. Okay. So we get this equation on the y side. All right. So so let's kind of get our bearings here. So t sine theta, why does t sine theta equal kq squared per d squared? Well, the sum of these two things equaled 0. So all of this boils down into that. Then over here, you have a t cosine theta minus mg equals 0, hence this boils down to that. Now I didn't say anything yet about where that came from. So let's pause here. Well, the numerator is still kq squared, right? The denominator, d squared, became 2L sine theta squared, okay? And so that comes from you have two of these chunks. Each one of those chunks is an L sine theta. Just by using the sine is going to be half of d times L. Okay, so this right here, sine of theta will be d over 2, the opposite over hypotenuse. Okay, so that means sine theta is going to be d over 2L, which means d is 2L sine theta. That's where that comes from. That's the trig. So now we can divide, go through all the process of solving for Q. And so here we compute all of that and come up with 750 nanocoulombs. So basically, you would need to solve the right hand, the y parts, solve it for t, and you're just plugging mg per cosine theta in for your t. Okay, so if we, this means that t, get my color straight, t would equal mg over cosine theta, and we would take that, plug it in for t, solve that for q. All right, so that's where that comes from. So you should be able to do that given your algebra thing. And so we get 750 nanocoulombs. And somewhere between some number of microcoulombs to some number of nanocoulombs, that's the range that typical charge transfers can happen for objects like this through friction, et cetera, et cetera. It's really you need a lot more friction. You need humongous interactions to obtain more charge than micro to nanocoulomb level charges. So that's what you get with tape. That's what you get with rubbing sticks with wool, pulling tape apart. You're going to get micro to nanocoulomb levels of charge. Usually no smaller than nano, but no bigger than micro. All right, be very hard to get it any other way. All right, that's a wrap.